As I mentioned, we were on the shores of the Monterey Bay yesterday, and I want to make a special thank you to Kristen Arndt, who is our office administrator. She was very instrumental in the logistics of that whole affair and got us there and got us equipped, and thank you so much, Cards. It's an absolute pleasure to have a longtime friend here who has come with this presentation before. Dr. John Ryan, of course, with MBARI, a regional scientist here, well known, but also internationally as well. And one of the things about John that I think is very special, especially in relationship to this presentation, is that he's really, this is sort of an example of environmental justice, I think, for all living things. When you try to create a just society, you try to give voice, don't you, to those who might not otherwise be heard, and that's exactly what John is doing here, and that's the marine mammals, in particular the whales, giving them a voice so we can hear it. This is an environment that they share with us. So this is a unique opportunity to get up close and personal with this by way of this presentation called Whale Song. And to have John with us is a real pleasure, so I'm going to turn it over to John now. Welcome, John.
Thank you, Mark. Testing 1, 2. Testing 1, 2. How's the volume? Good. You can hear me? No? Oh, yeah. Okay, we're working. Better? Moved it up a little. Okay, let me know. I can adjust further if needed, but good morning. And really great to celebrate Earth Day with you. And for this opportunity to share perspective from the deep, I decided to focus on listening for conservation. And the reason for that is as soon as we cross the boundary between the atmosphere and the ocean, the relative importance of light and sound flips. We can use light phenomenally well over great distances to see in the atmosphere. In the ocean, not so much. Dive down just 100 feet and almost all the light's gone. 99% of the light is gone in Monterey Bay when you're down 100 feet. In contrast, whales can communicate over hundreds of miles because sound travels that well in the ocean. And it travels nearly 5 times faster in water than it does in air. So we're going to explore this world of sound in air. It would be different if we were in water, and I want to do that. But not today. I guess we're not going to flood the sanctuary. And we're going to focus a fair amount today on the largest animal species ever to have existed, at least on this planet. The blue whale. Yeah. And by big, we mean, 90 feet long, 300,000 pounds or more. And imagine weighing 300,000 pounds, but feeling weightless. Wouldn't that be cool? They do. And the other reason we're going to focus on blue whales is because this particular region of the Northeast Pacific has a lot of excellent research on blue whales. And in order to understand their complex lives, we really need observations from very different perspectives. Listening is one of them, a very important one, as we'll explore. So, with that, we get these amazing views of these giants from the deck of a boat or maybe an aircraft, and they're at the surface at least for one very important purpose: to breathe. But it doesn't take long. When that animal departs the surface ocean, it doesn't take long in its dive before our eyes are not much use to us anymore. And the other key reason to focus on blue whales is because they are an endangered species. We use that term a lot, and it elicits care, compassion, concern. But what does that really mean for blue whales? Well, one study estimated the changes in population of blue whales around the globe that resulted from hunting, commercial hunting. And what you're looking at is those vertical bars is the catch. That's data. That's from the records of whaling ships. And for all those years, you're seeing how many animals were caught. And then the blue line with its dashed lines for uncertainty are an estimate of the population. And this is now the whole southern hemisphere. Population was reduced to less than 1% of its original due to hunting. And whenever you decimate a population that severely, it's really hard for it to come back. It just takes a long time. So here we are with the estimate in 2001 of still less than 1% of its original population size. And I've been working with a local, Ted Cheeseman, runs Happy Whale. I'll introduce his data later, but basically he developed a system where people who are out on whale watching boats can take their photos of the whale flukes and they send those in. And a machine learning algorithm analyzes the shape and coloration of the fluke and identifies which whale it is. Well, Ted also takes people on adventures to the Southern Ocean. And in going there for 25 years, he's seen blue whales on 2 occasions. So it's really severe in the Southern Hemisphere. The North Atlantic, you know, this is one of the key points. Endangered means different things in different places. The North Atlantic population was also severely decimated. However, as of 2001, they're doing better than the Southern Ocean. Instead of 1%, maybe 5%. And here in the Northeast Pacific, the story is even more encouraging. Because not only do we see the population hit a low, but after the end of commercial hunting, you see the population rise. And it's approaching half of its original size. So speaking of the encouragement we heard earlier, that is encouraging. And this is a region where the changes we make can have an impact on the recovery of this population. So another key aspect of the framework I want to introduce is this really good work by World Wildlife Fund, UC Santa Cruz, Ari Friedlander there, and Oregon State and University of Southampton. They worked together to develop this understanding of the whale superhighways in the global ocean. You know, they migrate really long distances, and along those migration paths, they encounter many threats. And so the only way we can mitigate those threats is to understand their pathways, how they move through the ocean. And so they did a wonderful job compiling for all these different whale species their superhighways, their corridors. And in this same report, in addition to the baseline knowledge on where the species live, they've identified the threats that these animals face along their paths. And the one I'm going to focus on initially is ship strikes. I mean, there are quite a few. There is climate change, which affects how the ecosystem can feed them, for example. Fisheries, where they get caught up in gear and get injured or killed. Strikes from large, fast-moving vessels. That's the primary threat to their recovery, really. There's pollution, chemical, plastic, underwater noise. We do study that. I won't focus on that today, though. Offshore exploration and coastal development, and of course whaling, which is largely ended for almost all species. But let's focus in on the ship strikes there. And what you're looking at in this map is shipping traffic. You know, we transport most of our goods on the ocean. So there are a lot of ships out there. And one study led by Megan McKenna, she's down at Stanford Hopkins right now, and they put tags on the back of a blue whale to understand how does this whale respond when a large ship is coming at it. And the answer is the whale's slowly submerged. And the problem is there's a lot more ship well below the surface, and the ship's moving very, very fast. So they don't take lateral evasive maneuvers. They didn't evolve around ships. So they aren't really well equipped to avoid being struck. And you know, it happens a fair amount. If they get struck at the bow of the ship, they usually get caught there and drown. And of course, the collision may break their spine as well. Or they might get sliced by props on the left there. So it really is a major threat. And so the research I want to show you, which was fairly recently published, is how we can use listening. How can we leverage the tremendous acoustic environment of the ocean that brings the sound to our recorder beautifully? We can hear a blue whale from anywhere within about a 10,000 square kilometer area, just for listening at one point. And how can we use that listening ability to help understand and protect blue whales? So first, let's look at how we're listening. We're listening through a cabled observatory, a 52-mile cable that runs from Moss Landing, which is where I work here. This is where MBARI is. That's my office right there. And this cable runs across the northern shelf, around Soquel Canyon. Don't want to run a cable over a canyon. And then you get, off Santa Cruz, you get to the edge of the shelf, continental shelf, and you go down onto the continental slope a little steeper. That feature down there is called Smooth Ridge, and that is the location where this fairly large infrastructure, here's the cable coming in from shore, here's where we plug in our science equipment. And you know, it's unlimited power and communications, which is a really great advantage in research. As we zoom away from the observatory, you can see it's kind of a natural geological amphitheater, open to the Pacific, to hear all the species that produce sound so we can know they're present, study their behavior. And just because it amazes me still to this day that we can go down into corrosive salt water under tremendous pressure, plug in a sensitive electronic device, and it just works. I'll show you how that works. We do that with a remotely operated vehicle. You know, for scale, this is one Mark Aiello. And here's the cable, the extension cord that will plug in to the observatory. And you can't see it well, you'll see it better in a minute, through the eyes of the ROV underwater, but this is the tripod on which sits a little hydrophone. Just a little microphone, underwater microphone. Little instrument, big data, about 2 terabytes per month, just listening to sound. And so here we are. Now we're down 900 meters depth on the continental slope. There's the observatory ahead of the vehicle. And there's the hydrophone sitting on top of its tripod with the extension cord in place. And there we are plugging in. Yeah, it is, the pilots are incredibly skillful. I could not do this. There it is. Yeah. There it is. Yeah, now we have connection to an electronic device that can listen to many species, the noise we produce, and the Earth. The Earth makes a lot of sound. So let's go toward the end. We've spooled out the cable because we want to get away from the noise of the observatory. Then we set it down. One small step for hydrophone. One giant leap for hydrophone kind. So that's how we're listening. Deep water outside Monterey Bay. Now what I've told you about so far is just an ordinary microphone, the same idea as this one. It measures a pressure signal, and that's what's strumming our eardrums. But what if that hydrophone could also measure the particle velocity caused by sound, 3-dimensional particle velocity? Then you could say the sound came from over there or over there. And that's really important because in order to protect a species, we need to know where it lives and how it lives. And so what I'm going to focus on in the initial study is data from those shrouded instruments. This is our collaborator at the Naval Postgraduate School, Paul Leary. He's responsible for the system we deployed on our observatory. And each of these is one of those acoustic vector sensors. And the study I'm going to show you is based only on one acoustic vector sensor. So we can say the whales are over there or over there. But if you have 2 acoustic vector sensors, you can get a bearing to a call from both of them, and where those bearings intersect, you have a point on the map. So that's what's coming next. And this is Vanessa Zobel. She's a NOAA Dr. Nancy Foster scholar who worked with us very recently for about 6 weeks, and she was involved in this deployment as well. So we're going to listen in on blue whales. What are those sounds we're actually tapping into to study the behavior of these giants? And the thing about blue whales, if you imagine your voice if you were 300,000 pounds, it's going to be in the bass section, definitely. And yet, if we want to hear, we say whales sing. They sing. What does that mean? That means they produce structured, rhythmic sequences of sound. And they'll repeat this for a really long time. But in order for us to hear the structure of the song, we'd have to be here all day because they're such slow singers. So what we'll do is we'll speed up humpback whale song by a factor of 10, just so you can hear and see the structure of the sound. So. Yeah, so you get a sense. It's 3 notes in this song, or at least 3 units, because these B calls, which is what we're going to focus on, the whales produce them the most, and they carry the most signal for us to analyze. So we focus on this one. Here's a simple arrangement, A, C, B. They mix it up. It might be an A with 15 Bs after it, and then stanzas like that. But now let's hear that same sound real time. So we don't need these. We need this. Crocodile Dundee would say, "That's not a speaker. This is a speaker." So here we go. We're only at half volume here. That's in air, that's pretty impressive. In water, it would be even more impressive because your body would be about the same density as the water that sound is moving through. You'd be completely transparent to it. It would just absorb you. So the first point I want to get to from research is studying that very song call is that blue whales move to the rhythm of the wind. The whole ecosystem here does, actually. So what does that mean? Well, this study I'm going to highlight was published last fall, and the reason I want you to see the author list is because I'm going to call each of them out to emphasize that, we need so many specializations coming together to do this type of research. People who model the transmission of sound through the ocean, people who put tags on the backs of whales so we can track them and observe their individual behavior, and so on. And let's start with that which is responsible for not only the invention of the wetsuit, and it is, coastal upwelling, but also for really fueling the tremendous productivity that this coastal ocean ecosystem experiences. What you're looking at is a view it's pieced together from many satellite images by NASA, and of course the land is fairly true color. The ocean has been enhanced because the ocean is a dark target, so they simply turned up the gain on the ocean so you can see the color. And what you see is near the coast, we are here, Central California, and blue water offshore. That means it doesn't have a lot of microscopic algae in it because there are no nutrients to grow. Near the coast, it's a lot greener, and that's because the winds drive an ocean circulation that causes deep water to come to the surface at the coast. And that deep water is like a compost pile. It's enriched in nutrients. And so when that nutrient-rich water reaches the sunlit surface layer, microscopic algae bloom, zooplankton, fish, and so on. The whole ecosystem spins up out of that. And that's what they call bottom up, you know. Fueling photosynthesis feeds the ecosystem, but there's another thing much more relevant to a blue whale. Blue whale is only one thing, one type of food, and that is krill. Small crustaceans, shrimp-like crustaceans. It turns out when the winds, upwelling favorable winds are out of the northwest here, and when they're blowing strongly, krill and anchovy school together. They form dense swarms. So if you are a whale that can open your mouth, have your pleated underside expand so that you take in a mass of water that weighs more than you, what you want to find is the places where there are massive, dense swarms of krill. And those swarms look like this. This image, video on the right is from when we took the ROV down to the continental shelf break where these krill swarms form. So you can imagine if you, I could swim around and get some of those, I think. But a whale that can just engulf all of that, and in a matter of 2 minutes squeeze out all that water and be left only with the krill, and do that feeding lunge 10 times on every breath hold. You know, that's the type of energy a massive animal like that has to bring in order to sustain its body, and to fuel long-distance migration, birthing, child rearing. You know what I mean? Yeah, so what we learned recently is that when the winds are relaxed, they're not strong, they're not out of the northwest, this scattering of color represents the distribution of anchovies and krill. You can see it's kind of light blue and dispersed. Then upwelling kicks in, and both anchovies start to form these really dense red patches. Red just means the acoustic signal bouncing off of those patches is strong, they're very dense. And this is what the whales are looking for. So we predicted blue whales, actually all of the baleen whales species have evolved to be able to find this type of resource in their environment. So we predicted that with that acoustic vector sensor that can point to where the whales are calling from, we said, we predict that when it's upwelling, blue whales will move into Monterey Bay because that's where the upwelling goes. These upwelling plumes in which the krill aggregate flow into the bay. So that's what we did. We tried to track their movements. And just to give you a sense of what upwelling really looks like, here's, this is from a fall study where you've got warmer waters in reds and yellows, cold waters in blues and purples, and Point Año Nuevo, where the elephant seals are, and the Sur Coast, those are sort of our upwelling centers. When the winds blow, the upwelling starts there and spreads throughout the ecosystem. So you can see these two upwelling centers getting stronger and merging, fertilizing the ecosystem and creating these krill swarms. So now let's see what we can learn from tracking the whales themselves by their voices. There's really 2 points here. The first one is you have to prove the technology works. So what we did is our Stanford collaborators put, I'll show you that picture in a minute, but they placed suction cup attached tags on the backs of blue whales. Big, long carbon fiber pole, and they slap the suction cups on and back away. And so right here, this white dot is a GPS position of a blue whale that had a tag on its back that it probably didn't notice. And this green beam is the sound, the direction that the sound came from according to this sensor on our cabled observatory. And we knew the whale was singing because the tag on the back of the whale told us it was singing. We matched the pattern of the song with what we received 20 seconds later at the observatory, and sure enough, we can trust this sensor to point to whales. That's the first point. It works. Now, what we can do with you have to know how far away can you hear a whale and accurately point to where it is. So this black contour here, it just sort of defines the boundary within which, if you are listening here, an animal anywhere within here, you can reliably point to where its voice came from. And so here's that upwelling plume at Point Año Nuevo, and you can already see it's coldest here at the point, and the plume is flowing into Monterey Bay. This is exactly one of those times when we would expect blue whales to converge on the bay. And so we're going to focus on this one because this upwelling plume at Point Sur flows southward outside of our boundary. Outside the boundary, we can reliably track them. So the first key point is that if you look at 2 years of data, these peaks in the total call activity coming from any direction, west, north, east, south, there's a peak at these directions pointing to Point Sur, this upwelling center, and Point Año Nuevo up here. So on average, the whales are hanging out more close to where the upwelling is starting at the coast. Now can we watch them move from day to day? Here you're looking at that same picture of the process of upwelling. There are upwelling plumes not just here, but also further down the coast where wind energy is being developed, the Morro Bay wind energy area. And during this period here of, just about 6 weeks, we have a measure of wind-driven upwelling. And let's just track this wind. It causes the ocean circulation at the coast. And if it's upwelling, what we'll see at this location right here at the mouth of Monterey Bay is that cold, dense water will run over our mooring. And this line here shows you that cold, dense water at the surface. Winds, ocean circulation, whales in the bay. So these black dots represent the proportion of calling from within the bay. So right away we can see one upwelling pulse, the ocean responds, the whales respond. Second upwelling event is a little more complex. It's a series of wind-driven events. The ocean responds, and the whales come into the bay. But here was the thing we didn't expect to learn. The other measure of where the whales are that we really care about is, are they in this habitat where these shipping lanes can cause a problem? So now the red circles are the percentage of calls coming from area where shipping lanes transect. And you can see when they're not in the bay, they're out in the shipping lanes. So, right away we knew from years ago people had concerns. People have been out on the water studying whales for decades where they're like, we're concerned that this is an area where whales may be getting struck. Now by listening, we've said, yeah, that's a real concern. We've seen now how they move. So the Monterey Bay National Marine Sanctuary just unanimously approved the first step, which is voluntary ship speed reductions. Because if you reduce the speed of the ships, number one, you give ships a longer time to spot animals and respond and avoid hitting them, and you give the animals more time to respond as well. So that's the idea. How do we take science into helping these populations to recover? Here off our coast, there are these two efforts with the sanctuary involved and NOAA, protecting blue whales and blue skies. And what they're doing is taking real-time information on sightings of whales and microphones picking up calls of whales to let ships know, hey, there are whales in the area. But what we want to do is give them a little better resource. Here's a map of where the whales are now. So that's where we're headed. I'm not done. No, I understand if you got to go. Yeah, okay, good. Yeah, I'm happy too. I love blue whales. So, and let me know, Gloria, if the cane is coming for me at any time. So the second thing I want to get across that we learned from listening is that blue whales cooperate. I mean, it's a big ocean. If you want to find those dense patches of krill, it's actually not an easy job at all. But what if, when you found it, you let everybody know? And you could do that really easily because your voice carries 100 miles. And all your friends can swim really fast. Faster than you, Cindy. What we learned in this study, this is led by Dave Cade, a graduate student at Stanford Hopkins. And what Dave did in his thesis was to bring together all the observations you really need. Where are the krill, where are the whales? But his study was the first to recognize something that's been happening and hasn't been noted before in a well, it just hasn't been noted before. They're called supergroups. Picture 40 blue whales within a 1 kilometer radius. A lot of blue whales. It's a lot of blue. What's that? Yeah, exactly. Well, you know, what we know from the study is that they came together for one reason. It was the ultimate foraging opportunity. Super giant thick layers of krill that they were feasting on. And it's such a tremendous resource that no one individual could exhaust it. So if they share information, then the next time they need a meal, they can be listening for their friends who have found it. And so on the right is a photograph of these blue whales streaming toward the location where they were gathering. And what we heard on our hydrophone on the observatory is that on the 2 occasions when these supergroups form, I mean, they were encountered opportunistically. Right? How do you know where they're going to form? But they were encountered, and each time we picked up an exceptionally high rate of calling from blue whales of a very specific type of call. And I'll play that in a moment, but it is known to be associated with foraging. What Dave found is this is the type of resource they were converging on, and what you're looking at is the steep topography of the shelf break. The red and yellow is that massive krill swarm. Whale not to size. Whale's much smaller compared to that, actually. But that was their feast. And here's that sound. Here's 3 examples of that sound that they put out. Yeah, it's a good one. So that's story 2. I've got one more blue whale story, and that is that they adapt to change. This ecosystem, as we heard earlier this morning, El Nino, La Nina, that's a very strong, actually global phenomenon. It has most of its energy in the tropical Pacific, but it has teleconnections that spread around the world and affect climate really everywhere. And yet, there are longer-term changes. The blob, that warm anomaly that affected the whole Northeast Pacific for years, you know, that had a tremendous effect on the ecosystem. So how do they adapt to change, and how can we hear that? Well, let's start at the end of the story. These 2 plots, just look at the one on the left. You're looking at 6 years of data, listening, and on the horizontal we have basically how productive was the ecosystem. Based on the winds bringing nutrients to the surface, how productive was the ecosystem? And on the vertical, we have the behavioral transition. When do blue whales decide, I've eaten enough, I'm going to now go to low latitudes for the breeding season? California, thank you for all the food. You know, that is what happens every year. And what you notice is this positive relationship. The more the ecosystem is feeding them, the later in the year they leave. And they have this body to store a tremendous amount of energy. So if the ecosystem is going to allow them to build up those energy stores that they need for long distance migration, they're doing it. This is just another measure of that productivity independent description, which just shows the strong relationship. So how did we learn about this? How did we notice this close attunement of the giants to the ecosystem? We saw it earlier on the time scale of days. The winds spin up, the whales move into the bay. This is years. How are they so responsive to the ecosystem? And so, in this brief story what you're looking at for a year, this year starts in May and goes through April, annual cycle, so that we can center the year on when we hear blue whales singing. They start singing in late summer, rises through the fall, drops off in the winter. Now the reason, interrupt at any time with questions, by the way, please. It rises up in the fall not because the whales weren't here in summer. They're here, they're just not singing. So it's a change in their behavior that causes the rise of song behavior. Then it goes away not because they stopped singing, but because they migrated to low latitudes. They're still singing their hearts out down here. We just can't hear them. But this is what we hear off California. Now here's the part I want to emphasize. The ratio of song that they produce during the night versus the day. So what you'll notice is it rises in the fall with the song, levels off, and then decreases. And when it gets, this line here is the so-called median, and when that drops below a value of 1, it means that they're singing more during the day. So we heard this, listening for years, this is a pattern in the population. What does it mean? The only way to know that is to look at behavior of the individuals. And here's that tagging I was talking about. Where this is Dave Cade, the person who led that last study I described. But there's the tag, suction cups, carbon fiber pole. And I've heard from the taggers that they'll get everything from no reaction whatsoever from the whale to a slight roll and an eyeball. Like, what are you doing?
John,
Yeah.
how fast do the whales travel typically?
How fast?
How fast do they? Because you said there was a 10-knot rule for the ships. How fast are the whales going in comparison?
When they're moving at top speed, that's an easy number to get. Like fin whales can cruise at 25 miles an hour. But most of the times when they're struck, it's probably, it may be when they're not. I guess we don't know enough what they're doing when they're struck. In fact, a big problem is we rarely see the ones that are struck. So all of our estimates of how many whales are killed by ship strikes are underestimates.
So when they're moving in for food, how fast do you think they go?
That's a good question. See, here with this is where the dual acoustic vector sensor system will allow me to put them on the map and calculate distance over time. Right now, all I can do is say bearing over time. I only know it's somewhere within my listening domain, and I can say it's over there, which is good. Couldn't do that before, but it'll be even better when I can say that is where the animal is, and then I'll get you those speeds. Yeah.
The noise we are hearing of the singing from your recordings, is that air coming through their vocal cords?
Yeah, great question. Yeah, how do they produce sound? Well, it's not unlike how we produce sound. It's different in a few ways. They don't have vocal cords that they use for sound production, but they have tissues that vibrate when they move air across them. But they're not releasing the air into the environment like we are. They can move air between air spaces, internal air spaces. And so they can make sound going forwards and backwards.
John, for our friends at home, could you repeat the questions when they do?
Oh yeah, repeat the questions. Okay. Mm-hmm.
Going back to your krill and the upwellings, and the whales somehow zooming in, do their sounds, the deep sounds, do they act as one radar? Do the whales, can they react to their sound hitting even if it's dispersed krill, and find out that's where the krill are?
Yeah.
And number two, do those sounds that the whales make have any influence or effect on the krill themselves?
We need you on our research team. So, yeah, those are great questions. The first one, are they using sound for echoic perception, as they call it? Well, usually there's this division between the odontocetes, the toothed whales, porpoises, dolphins, right? That's what they use. They are fully echolocating machines because they're not engulfment feeding, like large swarms of fish or krill. Instead, they're hunting individual prey, and they do that in a dark ocean with phenomenal sonar. They're really amazing. And when they're approaching for the grab, the toothy grab, you'll hear a buzz because they're increasing the rate at which they're putting them out to track the animal that's trying to get away from them. And my friend, really brief story, my friend who's a photographer, he gets in the ocean near whales, lets them come to him on their terms if they choose to, and then he takes such high resolution photographs that he can blow them up to life size. They're real. These photographs exist. They're amazing. Whole wall minke whale. But anyway, he was out photographing sperm whales for the first time, and this sperm whale came up and interrogated him as a sperm whale would, which is put so much sound into his body he thought it was going to vibrate apart. You know, really powerful. It's the loudest voice on the planet, the sperm whale or cachalot. Well, this sperm whale went down for a feeding dive. It came up with a squid tentacle hanging out of its mouth, and it approached him slowly and offered it to him. He regrets that he didn't start chewing on it right away, you know, because he wanted to show that he was with him, you know. But, you know, and he has amazing stories like that. I'm going on a tangent briefly, yes, but first time he was diving with humpback whales, it was a calf, curious calf that came over to him. And this calf is interacting with him, but being very gentle, not lifting its pectoral fin over his head so it wouldn't bop him. Then he feels pressure on his shoulder and he turns to see mom's 2-ton pectoral fin, just gently letting him know she's there. That's my baby. Who knows? But, and then last story, a friend who is a producer with BBC was out here for Big Blue Live, and he was out kayaking in front of our institute because he wanted to get up close and personal with these humpback whales that were foraging on schools of anchovies. Well, while he and his friend Charlotte were starting to head back to the safety of the shore, a wall of whale rose up right next to them, a full breech, 65,000-pound animal hanging over their heads. And it was caught from 2 angles. And among the things you could see from those angles were that, number one, when that whale at the apex of its breech saw the kayak, its eyes literally bugged out. It went, auga, you know, just like a cartoon. And then it rotated awkwardly to try to avoid crushing them. And its pectoral fin just clipped the front of the kayak, and the suction of that massive body pulled them and their kayak underwater. Empty surface, no people. 10 seconds later, 2 people, kayak, uninjured. And that takes agility. I mean, they're just really so considerate and anyway, I love whales. So in all that tangent, I lost your second question.
I think you answered it probably. It's with that low frequency sound, just kind of, you know, paralyze or immobilize the krill.
Yeah. One of my colleagues, Kelly Benoit Bird, she's an amazing acoustical ocean ecologist, and she uses active sonar to study the behavior of fish and krill and other species. Dolphins too. But anyway, that's her hypothesis, and we're testing it now. Do the krill respond to that sound you just heard by aggregating? Are they hurting their own krill? And that's an open question, so stay tuned. Steve.
When I'm swimming in like at Capitola, I'm swimming out there, I never hear these whales, and I know they're out there. Why wouldn't I be hearing them with my own ears rather than being picked up by a microphone? I can't hear this below my frequency.
Yeah, so great question, because most of our experience of ocean sound is when we're swimming near the coast. And we have the sound of surf break. We might have motorboats in some places snapping shrimp, etc. And if you're swimming, what time of year is this? Anytime?
In the time, my swimming time is sort of the summer to the fall, right when they should be the loudest.
Yeah, they should be getting there. Well, yeah, people who either swim in Hawaii or even on boats in Hawaii feeling it come through the hull, you definitely can. If you're close enough, you will hear and feel their sounds for sure. But here's the thing, we're listening in a very quiet environment of the deep sea. We don't have a lot of background noise, and this hydrophone is extremely sensitive. So, you know, if that whale was right next to me, I would be hugely impacted by its sound. But of course, sound falls off exponentially with distance. And this hydrophone, though, it can pick up the very quietest to the very loudest sound. We can hear rainfall at the surface 3,000 feet above. That's how sensitive it is.
You say they can be heard with your machines for 100 miles or something like that. That's because they're very sensitive. But we wouldn't be that sensitive.
We wouldn't, but if you were a whale, I bet you would be a lot more sensitive because you know that you evolved for that. And the fact that we saw whales streaming in over a large area, and people have documented call and response between whales over hundreds of miles. So they do hear each other over that scale.
But if we were swimming, we would not sensitize, we wouldn't be sensitive to anything like that. We'd have to be much closer.
If you could quiet all the other noise in the ocean, I bet you'd have a better shot at it. Yeah, I'll repeat the question. I forgot on that one. Anything else for now?
How has the massive storms we've been having this winter how has it affected the migration, the krill population, all of that? Because you were talking about all the El Nino and El Niño storms, I'm wondering how these massive storms we've had in the last few months have affected.
Yeah. Great question. Because we see these plumes from the coast and they're massive. They're occupying a large part of the nearshore ocean. The thing about winter, in addition to rain, is that it's kind of, you might say, somewhat of a downtime for the ecosystem, a quieter time. Why? Because the upwelling is weaker, the day length is shorter, and the productivity at the level of the microscopic algae is quieted. It's at a low level. And that's why the whales, you know, perhaps are not here in winter. You know, they're taking advantage of the, they're taking advantage. Can you still hear me all right? Or should I turn it back on? Gotta turn it on. It's back on. Was that the voice of God? Thank you. So yeah, winter's kind of quiet, and of course the whales are largely, at least the species we're studying are not really, most of the population is down south. So, you know, that said, we've seen impacts of these coastal runoff plumes very briefly. For example, the largest red tide bloom in Monterey Bay we've ever observed started at the coast after the first rain flush in a pool of agricultural nutrient-enriched water. That didn't cause the whole bloom because the ocean had to favor its expansion, but then what it caused is a seabird die-off. So we do have those land-sea connections, absolutely, that affect, you know, the vertebrates. Yes, Roland.
Is there any further understanding of the effects of climate change on upwelling?
Yeah, you know, one of the earliest theories was that, you know, the effects of climate change are different in different regions, right? Sea level is going to be affected more in some places than others. And the thing about this coastal upwelling is that it actually lowers sea level when it's happening. Why? Because the whole upper ocean is more dense. And when it's more dense, it occupies less space. And sea level is actually lower over this upwelled dense water. And so there was an idea that the changes in wind patterns could actually enhance upwelling, so that during at least part of the season, we might even see lower sea levels. And then in winter, when upwelling is not happening, of course, that offset wouldn't be there. But we haven't watched long enough to see it happen and to see if the winds really are going to, upwelling winds really will intensify, because those trace back to a large atmospheric high pressure cell over the Pacific that moves annually. And it's those changes at that scale that will affect a lot of what happens during at least part of the year off California. So, yes, Lynette.
So back to the whale strike spaceship. And the first thing I'm thinking of is if whales, we're listening, they're listening. Are there any studies being done that are similar to the things you put on their car for deers, so that they hear the ship coming?
Yeah, great question. An alert, you know, an early warning. Yeah. So the question is whether there's any way to alert whales ahead of a ship so they are less likely to get struck. You know, this is definitely beyond my realm of study, but my understanding is that how sound propagates near the surface with surface waves and mixing is different than how it propagates down deep. And it's trying to send a sound forward when the bow of your ship is itself creating a whole lot of noise and pressure variation. There could be some technology development there, yeah, to try to alert the whales. Then the question still becomes, if they hear that, do they recognize it as, I got to get out of the way, and do I know how to do that? And admittedly, it's only one study so far that I'm aware of, but the whale didn't try to get out of the way. Fortunately, it didn't get struck by the ship either. But, you know, I think the voluntary speed reductions, as simple a step as that is, can be very effective, and I'm glad the sanctuary has already approved that. The other thing is, I think you would want to get observers on ships, because, or even infrared cameras that scan the surface for spouts. Those stand out. And machine learning algorithm that says that's a whale spout, so the ship can respond. Mm-hmm. Yeah, things like that. And those technologies do exist, and people are trying. You know, there's hope.
Is there any talk of changing the shipping lanes, moving them?
It's already happened around San Francisco Bay for that very same reason. Down here, talk, yes. Action, yet, no. You know, ideally, people who are in the shipping industry, I think if they know about it, they care about it, and they can take actions. In fact, we need them at the table, absolutely. And there are a lot of ideas, and there's a person who lives here in SoCal. I was actually at his fundraiser yesterday. These whales have been on tour this weekend. We were at Ales for Whales at Humble Sea Brewery for California Ocean Alliance. And Brandon Southall, he was with NOAA during their ocean noise program build-up, and he brings together all the stakeholders internationally, including shipping companies, and that's what we need. People do care when they know. Mark?
Well, it's almost like that principle: pedestrians have the right of way ultimately, and maybe we should regard whales as pedestrians. I mean, in that way, and they should have that right. I mean, it would be nice if they understood the alerts, and if we had the technology to do that. But perhaps human beings, and especially those who operate ships, and the companies that supply them a job, and all those things, could maybe make that a part of their policy. Cooperation with scientists like you and those folks who gather this info.
Yeah, I agree. They have right of way, and in a way, that study led by World Wildlife Fund of the migration corridors or whale superhighways, that's kind of defining their right of way.
They kind of do that.
You can define where, and you know what time of year they're migrating on that highway. Right. So that's key information globally, because shipping is a global phenomenon. Right on.
This is supplied Caribbean, like cruises as well, cruise ships, not just shipping bags.
Cruise ships can move fast, sure. They're a threat too. There are much fewer of them than there are container vessels, cargo ships, and we did a brief study of actually noise produced by cruise vessels coming into Monterey Bay, because that was a concern, one of the concerns. And that's primarily the context we've thought about cruise ships. But yeah, any large vessel moving fast is a risk.
I wonder if it must be a reality with the Alaska cruises as well.
Oh yeah. Yeah, and and fortunately, I think because of ecotourism, when they get to a place where there are a lot of whales, they're moving slow, because that's their paying customers are looking for that.
Are there interspecies communications then?
Yeah, there's another story here I'm not going to get to, I can tell. I mean, I know I said you can ask questions, but people, let me... but I'm going to get to it, the shortcut, because of your excellent question. So the answer is, we've noticed that of the 3 species that put the most sound into this ocean here, bluefin and humpback, they have very different foraging strategies, and they can adapt to change differently. And what we found is that in a year when krill was abundant and fish were not, humpbacks, they can switch. You got krill today, I'm happy. You got fish today, I'm happy. Whereas blues and fins mostly only eat krill. So here's the point. In the year when krill were abundant, humpbacks were seen foraging with the blue whales to a greater degree, and the isotopic composition of their skin showed that they had been eating more krill. Then 2 years later, fish were abundant, krill were depleted, and blue whales, their signatures said they were hurting a bit for food, and humpbacks they had the fish signature. And so my point being that if humpback whales, they're so incredible in so many ways. They really are. But one way is their ability to adapt and maneuver. And in this case, I think take advantage of whatever foraging opportunity is there. And if blue whales are bellowing out those calls when they find a good place to forage, my hunch is a humpback whale will know how to find that. Yeah. But it's hard to know the complete answer, because you have to track the animals throughout their behaviors. And we're not there yet, but yeah. So how are we doing on time, Gloria?
Why don't we hold questions, and why don't you just finish your presentation, hold questions till the end of the, do you have some more of your presentation?
Oh, I got too much more, I think. So what should I finish up in 10 minutes, 5 minutes?
Yeah, how about
10 minutes. 10 minutes it is. So this is that story of what we learned from watching the individual. What you're looking at here is time on the horizontal. This is not quite a day. If its background is white, it's daytime, dusk, and nighttime. And what you can see is this vertical black line is the animal diving, coming up for air, diving, coming up for air, again and again. And everywhere you see a blue dot, the tag on the back of the whale recorded a feeding lunge. So all day it is stuffing krill. And then it gets toward dusk, and you still see foraging, these blue dots, but you also start to see song showing up, these green dots, song calls. So they tend to partition day and night between feeding and singing, and somewhat of a mix. Now take 600 or more hours of data from those tags, and what you see is that the song calls, which we saw were mostly at night, indeed, the night and the dusk dawn, that's when most of the calling is happening if you sample many whales with tags on their backs. What about foraging? It's the opposite. They're mostly foraging during the day. It's not either or, but it's definitely a tilt. Now let's track one blue whale from where it was first tagged, Gulf of the Farallones, and it made a really rapid transit over a month all the way down to Baja. And what you can see is during this first 10 days or so, the animal's staying at a fairly constant latitude. So it's hanging out up here. The circles represent the number of feeding lunges per day. If it's a bigger circle, more feeding. So all this time, the animal's up there feeding, and it's colored red, which means it's mostly feeding during the day. contrast, it's really only singing at night. The triangles are song. So this animal is definitely partitioning its day. I sing at night, I eat during the day. Then it starts heading south. Two things happen. It's not feeding at all anymore. No more circles. And you can see these triangles go from blue to red, starting to sing more during the day. So this is the individual level. Now when we go back to our microphone at the bottom of the sea, and we return to that shift we saw in the amount of singing night versus day, that's the sound of migration. When they shift back to singing more during the day, the population as a whole has shifted into migration to lower latitudes. And so that's how we were able to relate these, understand how closely attuned the animals are to their ecosystem. They'll stay here up to 4 months longer in any given year to forage. And when you think about their breeding season being only about 4 months, that's a major adaptation that they make every year.
I have to ask a question.
Yeah.
That, would we conclude then that their singing is associated with their navigation and their travel?
With their navigation and their travel, you know, it's...
More of that.
There's an amazing story. So the question is whether their singing is related to their navigation and travel. There's a story from the North Atlantic. A blue whale heading out of the North Sea went straight to a seamount that's deep below the surface. I mean, it went straight to it. Then it got to that seamount, it turned, and it went straight to another seamount. Either it has a very amazing map in its head, or it's using its sound to navigate. So I think it's the latter. I think they have an ability, since their voices propagate so far, they can sound out their environment quite well. And it is part of migration, I believe. So we're going to go, I'm going to shut off the science. Anybody who wants to stay and talk more science, I've got it. But this is really also about listening. And I'll get to why. Okay, they adapt to change. There's the Mysticete Symphony. Doesn't look like a song sheet. That's three whale species singing simultaneously, right here. Monterey Bay. Okay, John has way too much material. But you can't, it's better than not having enough. So now let's hear from other members of the Ocean's Chancel Choir. We don't want that on. So this is the second largest animal on the planet. It's a fairly sudden sound. Yeah, warning. It's a fin whale. And that's played at twice real time. So it pitched it up a little bit so this speaker can handle it. It's actually lower frequency. Yeah, it's an amazing voice. And they get, that's the percussion, you know. And they keep excellent timing. But sometimes they'll get fancy for a fin whale and they'll mix it up with slight pitch change and doublets instead of singles. Crazy. Some of these videos are used in an exhibit, and Noah has a message at the end. Now let's listen to, you know, this is the most amazing singer, 8-octave range, more than 8-octave range, the humpback. But we need to turn down 0 dB, we're going to go down a little bit. Turn this up. We'll have to stay here 7 minutes if we want to hear the whole song, so I'm going to speed it up for you. by a factor of 8, because that's the way you can hear the structure of the song. A song is composed of song units, the shortest sound you can hear, these are arranged into phrases, which are repeated as themes, and a collection of themes is a song. And a humpback whale might sing its song for 24 hours straight, just even timing its breathing to not interrupt the rhythm of the song. So let's hear this song sped up. And that's an easier way to hear them modulating pitch and changing up the phrase. And who else do we have here? Oh. We should hear the narration on that, Cindy, don't you think? Cindy narrated that clip for the NOAA Exploration Center video that we have. And another voice. Echolocation by a sperm whale, finding a squid. And one highlight, if you ask a whale watch naturalist how often they see a sperm whale, you'll get answers like I did, rarely, or about once every 5 years. We hear them half of all days we've been recording for the last 7 years. So they're essential to the biodiversity of this region, and we can know that by listening. This one's a little intense. Orcas. And I think maybe one more. Pacific white-sided dolphins. They bark underwater and sound travels well. We're hearing them at 3,000 feet outside the bay. And this really, I think, is my final message.
Alexa, ask Ocean Soundscape to play Humpback Whale.
Here is a 6 minute 43 seconds recording of a single humpback whale song. They can repeat their songs for many hours.
We did develop an Alexa skill so that people can hear the live stream and the recording library. And this is my friend demoing it, testing it out with his daughters. And I mean, it kind of really demonstrates, you know, when we hear the sounds of life, we recognize it and we resonate with it. And it's hard to feel connected to species that spend most of their time beneath the waves and beyond our senses. But when we can hear their voices, we can hear the sounds they produce and going about their lives, it's a way to feel connected with ocean life. And we really can't care about ocean life unless we feel that connection. So I feel like sound does that.
Have you detected any differences between male and female whale sounds?
Yeah, absolutely. So for example, you know that foraging call from the blue whale, the down sweep that ends with a good room shake? That's made by both males and females, whereas the rhythmic repeated sequences of sound are produced only by the male blue whales, for example. That's for example, yeah. And there's, of course, the males wouldn't do mother-calf communication, which is much more subtle and often intended to be quiet and cryptic because they're avoiding predators. They might even spend time in a lagoon because the lagoon absorbs their sound, right? The sound's bouncing a lot more in the shallow water and the bottom absorbs it. So they're safer from being detected or heard. It's like that, yeah.
To piggyback on that, is any one gender singing more than the other? Or do they both, male and female, sing, do the whale songs?
Yeah, I feel like males are kind of in your face about it, right? They're just, do males or females sing more? That's the question. Or vocalize more. It's, the males, it's thought largely to be associated with the breeding season because it peaks during the breeding season, as hormones do as well in males. So, you know, they're driven, you know, biologically to sing. And yet, there are so many other dimensions to it clearly because we hear song 11 months out of the year here. So if it's just about the breeding season, why do we hear it so much? And it's part of their culture. There's this amazing paper called Cultural Revolution in Humpback Whales. And here's the brief story. 2 whales from the Indian Ocean, singing their song, swam over to the Pacific. West side of Australia, east side of Australia. And they joined a population that had about 80 singers in it. And in the first year, the songs were the 2 and the 80. They were separate. The next year, about a quarter of the whales were singing the new song. Next year, about half. Eventually, the new song completely replaced the old one. That's cultural transmission. They're learning from each other. A population shares a song, but that song continuously evolves. And they might decide they like the newcomer song. Drop their own. Yeah.
Can you tell the age by the songs, like the juveniles or the babies?
Yeah, the songs is definitely, at least in the 3 species, bluefin, humpback, you know, it's the adult males that are singing. I suppose the juveniles, like human juveniles, got to be playing around with it. So, but there's some really cool things, though, really briefly. You can tell by the click of a sperm whale, you can tell how big it is. Just because of the attributes of the sound and how it's produced in their head. I think that's pretty amazing. But Stevie, did you have one? Oh yeah, I thought I heard you.
I'm just asking.
Yeah. Yeah. So anyway, on this Earth Day, it was fun to take a dive into the largest habitat on Earth with you, listen a little bit, and I guess the closing message is, you know, in science as in life, it is important to be a good listener.